Okay, so we're recording. We're going to take a look at problems 1 through 6 on the Chapter 2 exam review. So take it away with number 1.
Okay, so this is what we came up with number 1.
Okay.
So,
Can you walk us through how did you do it?
well, we basically just looked at points where the t was the same on each graph. So we started out like where t was 0, which is where x was -2, and y was 1.8, which was right here.
Okay.
And then we just kind of picked random points along each graph, like say where t was 1, which was where x was like -1.4 and y was about 2, which would be like right here, I think it was. So, and then from there on, we just kind of followed the same pattern all the way over to the end.
So x is -1.4 and y is 2. Can you show me again where that's at?
Let's see here, x is -1. Wait a minute. I may have goofed that up somewhere. Hang on a second.
No, it's okay. I think you're in the right spot. I think you were pointing at the wrong point.
I must have erased that point or something.
Yeah.
I think that would be like at 20 point. Hang on a second while I figure out what I did here.
You're trying really hard to make it that point, and it's not that point. So
I know.
if I just say plot the point -1.4, comma 2, you go -1.4 and then up to 2.
Oh,
and hey, yeah, so it's
must be
right
erased
about
that.
there.
I was looking for a dot.
Yep, exactly. And I knew that's what you were doing. You're like, I want it to be that point right there, and it's not a dot that you made. But this raises the important purpose of going from parametric to a phase plane graph, right? You have to trust that when you're reading at a particular t value, that corresponds to a point on the phase plane.
Yeah.
And so those are the places that you can guarantee exist. And then every place in between is just kind of filling in. And notice, he didn't just draw a straight line to connect one point to the next point, to the next point, to the next point. That would look really gross and wrong, right? That wouldn't be the proper curve. It would give us a general sense of what direction things are going, but it wouldn't be correct. It's like when Maple does its taking way too big a steps thing, and the curves just get all herky-jerky, right? So that would be the equivalent of what we're doing. We just have to take num steps and raise it up, or take step size and make it smaller.
And we also figured out that like the humps of the x are where it's farthest to the right, and the valleys of the x where it's farthest to the left.
Yep.
And the humps of the y are where it's highest, and the valleys of the y.
Yep. And so you should be able to spot those points. I should be able to look at your curve and say, I'm going to look for where it's the tallest. And that corresponds on the parametric graph to about, I don't know, like 1.8, something like that, somewhere in that area.
Okay, yeah.
Yeah. So a height of like a y value of at t equals 1.8, it's like a height of like 2.5. So yeah, ballpark, a little bit higher than that.
A little bit off there.
So yeah. So this is lovely job. Good job with that. Any questions on that from anybody else? Everybody clear on the process, the procedure that they underwent in order to produce this graph? Cool. Okay, how about number 2?
That would be us.
So number 2, we had 4 different sets of differential equations and 4 different phase plane graphs.
Correct. Do you want me to try to get the graphs up on the side, or do you think we're good?
I think we're good. People can take a look at the graphs on their own documents.
All right. So we said that A went to 2, then B went to 4, C to 1, and D to 3.
Okay, so if this, for example, were an exam paper, I would totally ding you at least 1 point for not filling in. There's a really important gap. You just have a line of code and an output, and then you just tell me that this one goes to 2.
Well, that's why this is a presentation.
Okay.
So
sneaky
the procedure
devil
here
Okay, so fill it in.
was to figure out, so we got some equations, right? We want to know, hey, where are these equal to 0? Because we can see the zeros all over our fancy stuff. And also that's what the instructions said to do, so that's what we had to do. So we used the solve command. We found where our differential equations were equal to 0. And then Maple said, hey, look, we got some points here. And then we went to our graphs and we said, well, 2 kind of looks like there's a hole or an equilibrium at about 1.5, 1.5, which is roughly pi over 2. So that's what we said. And then we rinsed and repeated for the rest of the problems. There were no contradictions with anybody, so we just kind of bada bing, bada boom.
So it's worth pointing out that for D, there appear to be two solutions, two equilibrium points. But what about B? What's going on with B?
Well, B, there's a root of thing. And so we just kind of like, we'll come back to that. And so using the process of elimination, we concluded that went to 4.
Okay. And so what are you thinking the root of thing means?
I don't know. You've explained it once before, but every time I see it, I just kind of avoid it. So, yeah.
So it's basically saying, imagine you have an equation that looks like z squared minus 2 equals 0. What are the solutions for that?
Plus and minus, what is it? Plus and minus square root of -2?
Plus or minus just square root of 2. But yeah. And so if you look at the graph, look at number 4, you can see when x equals -1, and give everybody a chance to click over and take a look at that on their graph. Or if you have it available, can you just share screen for that particular graph?
Pull one of these bad boys.
Oh, look at you, fancy.
Look at that.
Oh, so fancy. And so if you look at number 4, graph number 4, or graph number IV, you can see that when x equals -1, there are two equilibrium points. One of them is at a positive y value, and the other one is at a negative y value. Roughly, what would you say those positive and negative y values are?
Let me say roughly the square root of 2, probably.
Yeah. Which, by the way, the square root of 2 is ballpark what? Anybody know? I mean, you could ask Maple to tell you, but
1.41.
Yeah, it's like 1.4, 1.41. Yeah. And so if you look at it, it looks like it's at when x is -1, you can see there's this weird spot where there's stuff going on. There's swirly around there. There you go. Look at that. Lovely. You can totally tell that there's something weird happening at about just shy of positive 1.5 and negative 1.5. There's something weird happening at those heights. And so the interpretation of the root of is basically saying whatever's inside there, the z is a stand-in for some number. And so if you say that inside that parentheses, set that thing equal to 0, and those are the answers. I don't know why Maple doesn't just say plus or minus the square root of 2. It seems like it would be simpler to say that, but it actually has a purpose for more complicated answers and more complicated mathematics, especially when you're looking at, literally complex numbers. So sometimes it's not as easy to report the answer as to just say plus or minus square root of 2. Sometimes they're a little bit more complicated than that. So cool. And I think there was a second part for this. Was there a second part for this? It said, no, just find the equilibrium and then match them up.
Explain your reasoning. Yeah.
Okay. So I know that you were going to explain stuff and you were going to talk it through, but I do want to point out, when I ask a question that has words like explain or describe, and you don't use words in your answer, that's a bad sign, right? That is missing the fundamental part of the answer that I'm looking for, right? So make sure that you read the questions and you answer the question I'm asking, not the one you want to answer. Okay, so that's number 2. How about number 3?
That'd be us. Yeah, let me pull it up. 3. So, we had number 3, which was consider the system dx over dt equals 3x minus y squared, and dy over dt equals 2y, and then derive the general solution for the system using by hand analytical techniques. So here we are. So that's what we were given. And then we, by the, whatever it's called, the separation of terms,
Variables.
variables.
Yep.
We got that for y of t, and then we did the other side, or we did the other one, and we had to move the 3x over to the other side, and then we found mu, and then which was negative 3t, or e to the negative 3t, and then we multiplied that. We took e to the negative 3t, multiplied it by everything, and then we got the derivative of the derivative of e to the negative 3t times x is equal to negative c1 squared e to the t.
Now there was a little bit of simplification that you did right there, but I want to point out this is actually a spot where a lot of people make a mistake. They will square the e to the 2t, but they won't square the constant. And that constant, that's another factor in there. It's got to get squared as well. So they did it right. We have negative, the negative sitting out there is because it's negative y squared. And so when they put that in there, the negative doesn't go away because it gets squared. It's the y that's getting squared, not the negative. And so they squared the e to the 2t, that becomes e to the 4t. And then when they multiply by e to the negative 3t, that just leaves them with e to the t. So good job on that.
And then we took the integral of negative c1 squared e to the t. We got negative c1 squared e to the t plus c2. And then we got x of t equals negative c1 squared e 4t plus c2 e to the 3t. And then we, this is where we solved it just to make sure we got the right answer. But that's with the particular solution. So then part B says to state the solution that satisfies the initial condition. So we put 4 in for x of t and 2 in for y of t. And then we took, so 2 equals c to the 1. So then we put 2 in here. So we did right here, got negative that. So then we got negative 4 minus or plus C2, and then 8 equals C2. And then we came over here, double checked, and it was right.
Cool. Can you do me a favor real quick and remove the initial conditions on that desolve? Because I want to see what Maple spits out so that we can see the difference between that and what you guys came up with. So
you want me to just take the whole?
Yeah, just the inside. No. Yeah, just the backspace. There you go, all the way. One more. There you go, and just hit enter. Let's see what Maple says. So notice y of t is the easy one, and so Maple calls that C2 for some reason, and so that agrees with your y of t. But notice the general solution that Maple gives is not so simple, right? It doesn't give the exact answer that they came up with, even though their particular solution is 100% correct. And their general solution is 100% correct. So this is one of those examples where you could look for verification in Maple, and you might go, oh crap, I don't know if that's right. Is that the same thing that I got? And one of the only ways you might be able to tell is to force Maple to give you a particular solution by giving it initial conditions, right? So even if there was no part B for this problem where you didn't actually have to solve it for an initial condition, that is actually a really good way of checking. Because if you give it an initial condition and you get the same result as Maple does, then you should feel good about that.
Just do D, so.
Yep.
And there you go.
Yeah. So nice work.
So, yep. And then we have 4 as well.
You have 4 as well, so I'll take it away.
Here's 4. And 4 says, consider the system below as well as its corresponding phase plane shown on the right. So we did that. And that is why we have our parameters as -2 to 2, because that's what they have on the phase plane to the right. So there's that. And then so we just put it in a DE plot. So we have our 2 differential equations, and then our variables, and then we have our time t 0 to 5, and then we have our very different solution curves, and then we have our parameters, line colors, and yeah.
So how did you know that those initial conditions would result in very different solution curves? How were you able to tell?
So we picked the first one, and we had with x to so x was on the x-axis, and then the y was 0. So we knew it would be different. And then the next one we had x and y both not on the axis; they're both away from the axis. And then the third one, they were again both away from the axis, but in the opposite direction. So that's why.
Yeah. So one of the ways, probably the easiest way, is if you just create a DE plot without any initial conditions, like you already had it for this particular problem, it was given to you. So you could have
Yeah.
looked at that DE plot or the phase plane and said, if I choose an initial condition here and an initial condition over here, I'm probably going to get very different solution curves. But if you
Yeah.
chose an initial condition of 0, 2 and 0, 1, they're going to be
Yeah.
pretty much the same curve, right? They're going to be really boring. Not a whole lot of difference. When you're making a phase portrait, the whole point is to come up with as many different solution curves as you can. So nice work. One question for everybody real quick though. If we were to, in that first phase plane, if I were to say, take the t, and instead of going from 0 to 5, make it go from -2 to 5, how would that change this graph? This is a question for everybody, not for you, John, alone. John's going to do it here in a second, but he's going to change that to -2. So before he hits enter, I want you to, in your head, predict what you think is going to happen. What are you going to see that's going to be different?
I think the lines will be a little longer.
Okay, when you say the lines, you
The
mean
solution curves.
the solution curves. Okay, little longer. How? Which way? For example, the red one. What direction? The maroon one. Sorry.
I think it'll be go a little farther down.
Okay, so it's not going to go through the origin and out the other side.
Let's see, which one was that? No, it should go down farther.
Okay, so this is the kind of thing where you can pretty easily check in Maple. Go ahead and hit enter, John. Let's see what you get. Does it match your prediction? Notice the blue curve. It doesn't look that much different, but it actually does go a little bit further away from 2 in the positive x direction. And the green curve goes a little bit further out in the up direction. So what you're seeing is longer time, which means longer curve length, but it doesn't necessarily mean it's in one particular direction. It's in whatever direction that curve is going in the -t direction. So good job on that. Thank you. And let's take a look at B, part B.
Part B right here, and then it said describe the behavior over time of the solution satisfying the initial condition t x y equals 0, 0, 2. So that's what we did. We took out our other and we put in our 0, 0, 2, and we made it just green, and that's all we really did, and I plotted it.
Okay,
and
so
then
what? Go ahead, next part.
It said describe the behavior of it, and so the solution comes off the x-axis and goes towards the origin as time goes on.
Okay, some of you on that last exam, I really went to town on feedback, and that last problem set too. I really went to town on a particular mistake that got repeated a couple of different times, and I see evidence of that mistake in the description that we have here. And I paid John $5 before class to actually write this in there. So good job, John. I'll give you that $5 later. Anybody want to take a stab as to what that could possibly be? What would I comment on and ding points on for that response?
The description.
Something about the description. Yeah, there's something there.
Is it
It doesn't go off the y-axis. Is that right?
Well, I get what they're saying. They're saying the point starts on the y-axis and the solution curve moves away from the y-axis. It might be helpful to say which direction, right? Off the y-axis can be either direction, right? But
Is
that's
it
not the one that
because,
I'm thinking of. The one that it's a problem in terms of they said something incorrect. It's not just they left something out. They said something incorrectly.
is it because we said it went to the origin, but it just gets closer to it as time goes on?
Do you see the language? It goes to the origin. Does a solution curve on this phase plane ever get to the origin?
No.
No. How long would you have to wait for it to get to the origin?
An infinite amount of time?
Forever. Yeah.
Forever. It's you can think of it as an asymptote that's coming straight up out of the screen, right? Because as t approaches infinity, that curve is going to get closer and closer and closer to the origin. And what that looks like when we make a shadow on the phase plane is it looks like the curve's slowing down, slowing down, slowing down, slowing down, getting closer. And if we could kind of zoom in on that origin, you'd see that even as t goes from 0 to 5, we are not at the origin. If you were to change your window settings from x equals negative 0.01 to x equals, you would not see that solution curve approaching, right? It's not close enough. So we got to be really careful. The mathematics does not predict the solution curve ever gets to the origin. Because what is the solution curve? What is the initial condition for a solution curve that is at the origin? What initial condition would I have to use to see a solution curve at the origin?
The origin itself.
Yeah.
That's the only place, the only initial condition that is at the origin is the origin. Every other solution curve approaches it, but it never gets there. And this is, you might think, oh, you're just splitting hairs, but that's an important distinction. The distinction between function value is this and function value approaches this. That's the difference between pre-calculus, f of x is 2, and calculus, f of x approaches 2. Those are two very, very different interpretations. In mathematics, that's a big deal. But it's also a big deal in physics, in engineering, because if I ask you, what's the value, if I wait long enough, what is this thing going to become? And you tell me it's going to become 2, but it's not actually going to be 2. It's going to approach 2. That's a really important distinction. Right? We might think, oh, it's close enough where you can't measure the difference between it and 2 anymore. That's a measurement problem. That's not a math problem. That's just a measurement problem.
Doesn't it equal to when t equals infinity? Like they do intersect at infinity though, right?
Yes, but
Okay.
remember, infinity is off campus, and so we can't talk about it. Right?
Oh, fair enough.
No, infinity is a direction, not a location. You can't put a point at infinity. And so as a result, we just say, sorry, it's not possible to see that.
So you can't say f of x equals 2 when t equals infinity. Like that's not.
Or when x equals infinity. No, you can't. You can say f of x approaches 2 as x approaches infinity. That's a legitimate way of saying, I think what you intend. Does that make sense? The distinction, I want to make sure that that distinction is clear, and that's one of the purposes of that particular problem, is I wanted to make sure linguistically that we're talking the same language. We have to use the language of calculus when we talk about approaching a value. Okay? How are you feeling about that? Okay. Cool. So that's part B. I think you guys are done.
Yes, sir.
How about number 5?
right, so for number 5, we had the what was it? The second derivative plus 6, the first derivative plus 8y equals 0, and you wanted us to where'd that page go?
Yeah, this is one where you're going to solve it using the lucky guess, the guess and test method.
Guess and test method, yeah. So for starters, I wrote it out in simpler forms: y double prime plus 6y prime plus 8y equals 0. And then we guessed y equals e to the st, and I kind of got this out of the notes because the problem from the notes from the example is pretty similar to it.
Mm-hmm.
And then we evaluate, so y prime equals e equals se s of t, and then y double prime equals s squared e s of t. So that way we can plug those back in. We checked the guess and the v, so we plugged those back in. And then we were able to actually pull e s of t out, and so you can see right here how we pulled it out. But however, e s of t cannot equal 0. So then we performed factoring right here. So s plus 4, s plus 2 equals 0. And then that gave us our s's. So we had our first y1 of t, which was our first one, is e equals -4 to the t, and then y2 of t is e to the -2t, and that was our 2 solutions. I'm not sure. I was kind of confused about putting that in. So like I performed the DSolve to verify and make sure it was correct and stuff. And this is what I got for my answer for DSolve. And it was pretty similar, other than the fact that there was constant 1 and constant 2, and I had no idea what those were. So I just put that up there.
So you stumbled across something that we're going to get to in chapter 3. It's this idea of, hey, we found these 2 particular solutions. Notice there's no constants, unknown constants in y1 and y2. It's just e to the -4t. And if you take that, plug it in for y, it is a solution for that differential equation. Same thing with y2. But they are particular solutions. And it turns out that those 2 solutions, those 2 particular solutions, if you throw a constant in front of them and then add them together, you get the general solution, which is just crazy. It doesn't seem like it should work. But that absolutely is the general solution for this differential equation. That wasn't part of this problem. I only wanted you to get y1 and y2, and that was good enough. But you nailed it. So you got part A, and then part B says?
Yeah, part B. So I got so focused on part A and stuff, and I got done with part A, and I forgot that there was a part B and stuff. So I was kind of like sticking around with Steven and Bryce on there when they were doing their problems and stuff, and I completely forgot about doing part B.
That's okay. So part B says, can we convert that second order differential equation into a system of first order differential equations?
I think so.
I think I might have B.
Okay.
Here, also.
Let me share.
Give it a shot.
I didn't do any like actual explanation in my maple.
That's okay. That's okay.
So I just wrote it up here. The initial second order differential equation.
Mm-hmm.
And then I went through it, and I just first started off by saying dy dt is equal to v of t.
Yep.
And then I know that this guy right here is just the derivative of the velocity, so acceleration. So I just said dv of t over dt is equal to negative 6v and plus subtracted by 8y of t.
Yeah, that's 100% correct. The only thing that I would say, just to make it clear, at the very top, your second order differential is not an equation. That's all equal to 0.
Oh,
right?
Sure.
And that's what allows us to say, oh, and so if it's equal to 0, then we can move things from one side to the other.
Okay,
so,
there you go.
So absolutely. Yep. So nice work. So we have dy dt equals v, and the other one is dv dt equals negative 6v minus 8y. So nailed it. And of course, if we wanted to, we could take that system and find a DE plot for it, right? We could create a DE plot for that system, and we could take a look at what different solutions look like in that system. So nice work. Good job. How about number 6? Number 6, deceptively short. So it must be really easy, right? The ones that are always short, those are the ones you're like, oh shit, this is going to require a lot of explaining, isn't it?
We were unsuccessful.
Oh, I wouldn't say that. I think you guys were successful.
We can show you what we have.
Sure, fire away. The question says you've got completely decoupled system, and that is kind of textbook decoupled system. Dy d or dx dt equals some function of x, and dy dt equals some function of y. Now, we think of decoupled as being really easy to solve. That doesn't mean that they're really easy to solve, but that means that you could solve using separation of variables without any trouble. Dx dt equals something and dy dt equals something else. So what'd you guys do?
So we graphed a whole bunch of equations trying to find a pattern in the phase
Sure.
portrait. And so we did dx dt equals x of t and dy dt equals y of t.
So standard, really super straightforward.
Real, yeah, simple. And then we did x squared and y squared.
A little different. So at this point, you were thinking, what? What do the phase planes have in common?
We weren't sure yet. These two looked like they were both kind of symmetric about the origin.
Okay, symmetric about the origin. That's a good one. Got it.
Then the next one we did x minus 4 and 5y. And then that kind of threw our theory to the wind.
Wah. It's not symmetric about the origin anymore.
Yeah.
So what does this have in common with the other graphs that you've noticed?
So yeah, we're not sure. And then we did x cubed and y squared.
Ooh, fancy.
Yeah. And then we tried x. Oh, never mind that one. That one's no good.
Yeah. Pay no attention to this.
Neither is that one. We'll get to the left.
Okay, so pay no attention to those.
Those were not decoupled.
Okay.
So we were baffled. We could not come up with an explanation as to what special features do they all have. So.
Well, I like your idea of the fact that there's some kind of symmetry going on, right? And so this graph, you can see that there's kind of symmetry across the y-axis. It kind of looks the same on both sides of the y-axis.
It does. And this one kind of looks the same about the x-axis.
Yeah.
Which was what was throwing us because they didn't seem to follow a pattern. And this one was symmetric about kind of the origin, although not really.
Yeah, sort of. I mean, it's symmetric about the origin in terms of the, if you had to draw curves, the curves would appear to be symmetric, not the direction that they're going necessarily.
Yeah,
but
they're all going this way.
Yeah.
And we were working on the theory that maybe all the arrows were pointing towards the equilibrium point or away from the equilibrium point, but that didn't pan out either.
Okay.
We kept finding examples that did not work.
Yeah. So for that one right there, there's one equilibrium point, and that's it. Oh, that's 0, 0.
Oh, sorry, okay.
Wow. That's an old-timey alarm clock.
Hang on, I'm going to mute for a bit.
Okay. Wow. So needless to say, those questions that are asking kind of what do you notice, what features do they always have? Notice it doesn't say what do they have in common, it says what do they always have. So at this point, you could say, well, it appears that they always have an equilibrium point, right? Because if f of x can equal 0 and f of y can equal 0, there's going to be an equilibrium point at that location, wherever f of x equals 0 and f of y equals 0. Now, notice the problems or the examples that they came up with, at least the first couple, f of x only had one root, if you want to think of it that way, and f of y only had 1, 0. But you could make a function that has multiple, like if you tried something like f of x equals sine x and f of y equals cosine y. Can you pull up your Maple, Paul, and we'll try it again?
Yeah.
You can even turn your alarm clock on if you want. That's fine too.
Okay, so I missed some of that. My internet was cutting out. So what now?
It's okay. We were just talking about how cool you were. If you go to any one of these examples and type in, yeah. So for this one, instead of x squared, let's make it sine of x of t.
Find the sign here. Whoops.
Just, yeah, undo, back it up, and then x of t.
Should I do
And
x
then-
of t squared or just?
No, just get rid of the x of t squared, and then close parentheses, and then hit enter, and then for y, we'll just do the same thing. Instead of sine, we'll make this one, I don't know, cosine. So back it up and make it equals cosine of y of t. Now we know going into this that there's an infinite number of zeros for sine and for cosine. So when we take a look at the DE plot, we expect to see an infinite number of, oh, look at you unassigning everything. Ooh. Yeah, if you hit enter, it's just going to overwrite whatever the assigning was. So it should work.
Whoa, that one looks good.
So what are we seeing? What is it that we're noticing about our phase plane here?
Let's see. I think these. So it looks like there's multiple equilibrium points. Looks like, or maybe like. Pi over 2 and 0 might be one.
Yep.
Yeah.
Notice 0, 0 is not an equilibrium point. 0 comma pi is not an equilibrium point. Pi comma 0, not an equilibrium point. But there are some pretty substantial ones. If you notice, if you go to the right out to about 3, a little bit past 3, there appears to be x coordinate for a bunch of equilibrium points. And vertically, if you go up, not quite to 2, but definitely more than 1.5. So somewhere in the area of maybe pi over 2, you get an equilibrium point there. And if you were to back up or extend the time for your graph, you could actually see what happens to that solution if you play the clock backwards and forwards. Take a look at what happens to your solution curve. So it's almost like things are running away from one equilibrium point, but heading to another one.
Yeah, that's the way it looks. Yeah.
So here's an example that kind of complicates things. Now, the origin is definitely not an equilibrium point, and there's more than one equilibrium point.
Yeah.
But the equilibrium points exist at very particular locations that are obvious, because the x coordinate of the equilibrium points are always the places where f of x equals 0. And the vertical locations are always the places where f of y equals 0. Or yeah, f of y equals 0. I should have named them f of x and g of x or something, or g of y. I shouldn't have called them both f, because they're not technically the same function. They don't have to be. But. So as you start looking at these things, looking for patterns, looking for kind of particular traits or characteristics, that's a time-consuming process. Way more time-consuming than doing algebra. And it's also hard work, because you have to pay attention and notice things and look for patterns. And Paul and Emma were in there like, oh, let's try this system. Let's take a look at this. Let's take a look at that. So it's hard work looking for patterns. So one more thing that I would suggest for that one is you've expanded by looking at a simple, just standard, these things are the exact same function. And then you looked at things that were different, but they were always decoupled. And so being able to do +1 or +2 or plus a constant on those kind of does the shift. It shifts things vertically and horizontally. It shifts where the equilibrium points are, but it doesn't change those particular equilibrium locations. The shape of the DE plot, the shape of the phase plane, would be the same, but it would just be shifted this way or shifted this way. So if you look at that same graph with the dx dt is equal to sine x plus 1, and the other one, and just leave the dy dt alone, you would notice the x coordinate for all those equilibrium points would shift. So it would look like the exact same phase plane, just shifted.
Yeah, that makes sense.
Yeah. Cool. There's one more problem that we didn't get time to do, and we're not going to have time to do it. But you'll notice number 7 is a bigger problem. That's one of the reasons why I didn't assign it, because I didn't want one group to get mired in like 5 parts for this thing. But take a look at number 5. I'll pull it up on the screen so we can share this. Take a look at number 5, and let's see if I can. That one. That's the one. So taking a look at this thing, if I bump up the size, this is asking us to do Euler's method, but also to make a vector field, to produce a phase portrait, and then finally we get to Euler's method, right? So there's a lot of Maple work on that. Some things to think about when you're doing Maple work. Make sure things are nice and neat and tidy. You've seen a couple of people, I think most everybody today was using those kind of click, open up the kind of, I don't know what you'd call them. What would you call those things where you click on the arrow and it drops down? It's like a drop down menu kind of thing.
A palette?
No, not the palette, actually in the document itself, but it's the same effect. You know how the palette, you click on the little sideways triangle and it drops down? You can make those in Maple for your work to kind of keep things all together in one clump, in one chunk. So doing that is one way of organizing your work. And that helps me because then I can open up, I'll just open up question 7. That's the only one I want to take a look at right now. Another thing to think about when you're doing the Maple work is pay close attention to not just the equations and making sure you're entering the equations right, but pay attention to the precise value of those initial conditions, the precise value of all those parameters that I'm giving you, right? You don't want to screw everything up later on in the problem because you read 1, 1 in here and then you hop on Maple and you type in 1, 2 for your initial condition. That would throw everything off for the rest of the problem. So double check. Just go back through, take a second and say, did I type this in right? Is this correct? You'd be surprised on how many mistakes you'll catch that way. And then of course, knowing the code, what to type in for the code. So hopefully you're prepared and you've got your little glossary of code for how to type this stuff in Maple. But this one later on asks you to, there's that word, discuss. That means I'm looking for an explanation more than just it goes to 0, right? I'm actually looking for an explanation of what's going on. And then the last one, notice, using Maple, create a plot of the actual solution. The actual solution means in a DE plot, you can predict where this thing goes. By the way, if you try to type in this system of equations and de-solve it, it doesn't work. Maple can't solve this system of equations analytically. It can approximate it on a DE plot. It can approximate it with a numerical solution, but it cannot solve this straight up analytically. So if you're looking for an equation to plug things into, it's not going to work. That's one of the reasons that we make sure we know how to use Euler's method. So that's all I wanted to say about that one. Plus, I don't want to give away the store, but that looks an awful lot like one of the problems I gave you on the exam. So I'm going to stop sharing at this point, and I'm going to stop the recording here, but I wanted to say a couple of things that are on the agenda, a couple of things that are important. Number one, I will send groups that are done with investigation 2 and have it posted. I will send you your exams. So you don't get an exam until you've posted your investigation number 2. Sneaky. The other thing is the exam is due when?
Sunday night.
Sunday.
Sunday, not Monday. I want you to be done with this by Sunday because I actually do have a little something for you to do before class on Monday. Before class on Monday, you'll notice down at the bottom of the agenda, it says complete the matrix interlude, which is really just the first couple of pages of the 3.1 notes. And it's sort of a little primer or primer, depending on how you want to say it, about using matrices and the way in which we write matrices and do arithmetic with matrices. So it's just you filling in the notes. So you're going to do that before class on Monday, so that when we come to class on Monday, the first thing we can talk about is, hey, did you have any questions on that? I am not going to post the completed version of those notes. You got to do them. And I'm not going to do a video for this. This is something that you can do. You can walk through and fill in those notes. So old school, right? No video, just filling in the notes. So when you turn in your exam by Monday night, you'll have a little bit of time to do that. But I think most of you will be able to get the exam done before Sunday night. So I think that's it. If you have any questions or you want to ask me anything or talk to me about anything, you can stick around afterwards. Otherwise, we're going to hit stop on the record, and then I will see you all later.